this is a property of the system. Alright? And here comes the magic. Let's keep this function here. And let's recover the function in time. What would you do? You apply the inverse transform to both sides, and then you recover the response of the system. Can you see how beautiful this thing is? It's amazing. If you happen to have the transfer function of the system, and you can define the force as a complex variable, you organize the information in this way, apply the inverse transform, Laplace transform, and you recover the response in time. Easy peasy, isn't it? It's amazing. What we are doing is actually this. Remember, zero initial conditions, Laplace transform the output, Laplace transform the input, and there you go. This is what we ended up with. Any questions, guys? This is supposed to be quite interactive or dynamic, so if you have a question, please let me know. I probably I'm speaking something that might make no sense, and you might be better prepared to explain the sense. But anyway, let's move on. Given this, as I mentioned, you just apply the inverse Laplace transform, and then you recover the output. The output is given in time. Notice that I have put here ut. Ut is a step function that says this is going to be equals to 1 for t larger or equal 0, and this is going to be 0 for t lower than 0. So that means that we are putting a restriction on the output. This output is going to be measured only in positive time. That's the meaning of that u. But if you are happy to agree with this previously, we can actually neglect this, and we are left with the inverse Laplace transform of this complex domain output. It's just the output in the time domain. How is this defined? Well, we have this very terrible equation that you probably know better than I do how to use it, right? Do you need to use this to get the inverse Laplace transform? Have you ever used this thing? What do you do to get the inverse Laplace transform? Use the tables, use information that people have covered during the past years. Right? So we don't need to use this. This is the definition, absolutely. But somebody has had the time to put here several functions, perform the integration, and create a set of information that we can use now. Is that clear, guys? Perfect. So let's go to what we are doing now. We have been doing the analysis of this system when we have harmonic inputs. So let's assume that this is harmonic, right? How does a harmonic input look like? Like this. We are introducing an analysis for general loading because this function can be anything. Right? Can be the Laplace function of an exponential input, could be a step input, could be a constant input, a sinusoidal, a cosine, a parabola, or else, plenty of functions, right? This could be anything. Let's assume that this is just a harmonic in order to see what we have. That being said, do you guys remember how does this is ft equals cosine AT? Do you remember what this look like? Again, you don't need to do the whole integration because that's horrible. Use the table. Do you remember? S on the top, a squared plus s squared, right? you have the time, you can prove this. Use the definition of the Laplace transform and you can prove it. There's no need to do that. That being said, if this is a force, the only thing that is missing is this constant, isn't it? Right, so you can take this out. This is multiplied by FO as x squared plus s squared. However, what is equivalent to A in this equation? Omega, isn't it? What's omega? This is the input frequency, the driving frequency of the system. Great. Now, the next thing to be done, or redundant, just put in a better symbology. The next thing to be done is to look on the tables if you have a time domain function for this, applying the inverse. If you have a look to the tables, you will waste your time because there are no functions that are already expressed like this. What should you do in order to actually find the correct function time domain? That's one of the approaches that you might follow. Partial fractions, right? So you can say that this is going to be equal to some constant on the top that we don't know, equals to probably s squared plus omega squared plus b over whatever thing we have here. I don't know. Somebody has done it already. We're just going to use that information because we are not concerned on the theory behind. You know that already. If you do that, you ended up with something like this, right? If you check on the tables, and you get the fractional portion, partial fractions, and then you get on the tables, you ended up with this horrible thing. Does this look like what we have done already? Not quite. But if the time t tends to the infinite, what happens with these functions? They decay in time, right? So we can get rid of the whole thing here, because eventually they decay in time due to the damping, right? So therefore, this being a general solution now is going to be converted to a particular solution when t tends to the infinite. And if that is true, you can do some arrangement regarding to whatever thing you have here. You ended up with this. Is this known already? This is a particular solution for a system. And we got this solution with two analyses. Using trigonometry, using the complex notation, and now we are using the Laplace transform to get the very same thing. But what is the advantage of the Laplace approach? This is defined for any input. Here we happen to use the cosine because it's a harmonic input that we have been dealing with. However, Laplace works for any type of input. Is that clear, guys? Perfect. I do sincerely hope that these slides were updated when I did my check them. And they are in. Don't worry. Now, let's try to find what is the Laplace transform of the system if we do have these initial conditions. Right? You can prove that this is true. You just can take the Laplace transform on the left-hand side, take the Laplace transform on the right-hand side, which is this thing. And then you put the whole thing here, you group them to xs, and then you ended up with this set of data. This is something that we have covered already. And this is something that we haven't, but we can check into how does this table look like. This is taken from one of the books in the bibliography, which is the RAW, Mechanical Vibrations. And I happen to use that book for two things. First, it's quite academic. I happen to do derivations of the whole things. However, it's too academic. The problems of applications are very simplistic. But anyway, it can be useful for explaining at least the theory. And the second thing is that they have information such as these tables. This is a very extensive table, one of the annex. And as you can see, given the Laplace transform in terms of S, you can recover the time domain function. So for example, in this set of data, this function and this function here look like something like this, right? This is one of them, and the other one was this, am I right? And then you check this one. So this, or something that you can directly get from the tables. However, still, I am very reluctant to use the whole information given the initial conditions. Because if we set the initial conditions to be 0, we can deal with the transfer function. At the moment, we cannot define any transfer function, right? Because we do have some initial conditions. Get rid of them. If the problem is not simple, make it simple. That's our task. These initial conditions are 0, so therefore you ended up with something like this. The Laplace transform of the output equals to the transfer function times the Laplace transform of the input. Between these two things, this is something that you know already, because you know the system, which is something like this. Of course, we have a different form, right? It was something like this, m s squared plus cs plus k, or something like this. But you know that c over m equals 2 times this, and omega n equals square root of k over m. Use this information, put them here, and you ended up with something like this, right? Don't let me prove it. Probably I made a mistake. Okay, guys, any questions so far? All in all, the only thing that we are saying, establish null boundary conditions or initial conditions. You ended up with this equation, but this is actually expressed in this term. It has a meaning. The whole thing, as it is here, doesn't have any meaning, but if you separate this term and this, you get the transfer function times the Laplace transform of the input. So what is left? In order to solve this, what would you do? Take the Laplace transform of this and take the Laplace transform of the whole thing, the inverse. What's the most interesting thing to occur? We will see in the next slide. If you take the inverse Laplace transform of this function, you ended up with the response in the time domain. And this is done just taking the inverse Laplace transform of this product of two Laplace transforms. Right? It's like a game of words. And this is interesting. Look up on the tables. And this, the inverse Laplace transform of the product of two functions of S is equal to the integral in time from 0 to up to a time t of the function of time of the first one and the function of time of the second one. But the difference between these two is that there is a shift. The shift, the difference in time, or delay if you want, is given by this. This is actually a shift. If this is defined in t, this is a shift. This is not defined in t or in tau, this is the shift. Okay? Have you seen something like this already? Where have you seen that? You haven't. This is disappointing. Where have you seen that thing, guys? When did you take an EDO course? Was it last semester? 2 semesters ago? 2 semesters ago? Long time ago, right? So enough time to forget everything. I taught this course 18 years ago and I forgot that as well, so I don't blame you. If you look up at the books, this function,
what is the meaning of this?
this, the Laplace transform of this thing is just this function of the right. And the Laplace transform of this thing should be on time. But the definition of this product, if you take the inverse Laplace transform of this product, is given by the product of the functions of time. And you integrate this with respect to this variable, which is a variable of time. However, there's a difference. You don't express directly the function of time for the two. You express them with this variable, and this variable produces a shift, a difference in time, or a delay. You can see here, this is a function of time minus some time. So if you're analyzing what happened in the time t, this function tells you what happened in the time t minus this tau. This is a delay. So what happened a bit earlier, a bit before, depending on this value. Right? I do understand that it's very confusing once you see this for the very first time. And on my old days, nobody cared on animations or trying to visualize these things. And now I do care that you understand this. This is the definition. You integrate tau, and then we're going to see what you get. This form can be expressed in this notation. And this does not mean multiplication. This notation means convolution. Have you heard that? No. Are you serious? You have, right? In a program of differential equation, this is probably something that you have to care. But if you haven't, don't worry. Just learn a new concept. The convolution of two functions is defined by this integral. And this integral actually represents the Laplace transform inverse of the product of two functions expressed in the Laplace domain. All right? We have defined a new concept. The convolution of functions. You haven't heard, but you use quite often. Do you guys enjoy using ChatGPT? Artificial intelligence algorithms, machine learning. Have you heard about that? Image processing, sound processing. Have you heard? It's just this convolution. The thing is that nowadays we have a computing capability to perform convolutions in a quick time. Right? That's why this is quite important. However, this was developed ages ago. If you haven't heard about this, don't worry. Let's establish a new concept. Let's say that the Laplace transform inverse of the product of two Laplace functions is going to be equal to this integral. And this integral, this notation is just the convolution of this function with respect to this one, or all the way around. We're going to see how we use it. This is the convolution. This is a function f. The red one is a function f. So that means that the function f is a constant in this domain, and the function g is a constant in this domain. Right? Forget about the thing that is moving. Don't pay attention to it. Can you see it, guys? This is a function in time. This is time. This is another function in time. And this function happens to be constant in this domain. This is constant in this domain. And 0 everywhere else. Okay? Now, let's fix this function. This is a unit function. Let's go to fix this thing in space. This is fixed. And this is going to be shifted. Move a bit earlier and move a bit forward, depending on the value of tau. And tau could be anything between the minus infinite to plus infinite in the time domain. Right? So let's move the value of tau in order to move the whole equation. This is shift. This is a shift. Right? There is a delay when the function is here. And there was and now this is the delay with respect to this one when this moves forward. Okay? So let's pay attention now. What happens? How does this function look like when t changes? If tau eventually starts touching the beginning of the first one, take the product and an area is created. The area, you can see, is plotted at every instant of tau. So here, this area starts increasing. Can you see it? Increases, remains constant, decreases. And this function in black is the convolution of these two. Let's have a look to this. This is one function f. This is another function g. And this is the shift function. But you can see, this is not only shift. This happened to be put as an image of it because of the definition. We define t minus tau, whereas here they have defined tau minus t. This means that the function is all the way around. And depending on the value of this t, this function can move in time. And once this products this one, an area is created, you can see that the area starts increasing and eventually starts reducing. The area under the curve is the integral of the product, the thing that we are analyzing here. And this is convolution. If you don't get it, don't pay that much attention because you just need the definition of it. Using that, just for making the things easier, let's going to use this notation. This is the transfer function. We are going to say Fs, S stands for system, is the transfer function. And this Fs here was the Laplace transform of the input. We are going to define this as Fi for input, just for the notation. Because once we get this in time domain, this is going to be t small. The small t is going to be confusing with time. In order to avoid this, let's step. One property of convolution is that they are commutative. The convolution of these two in that order is the same as the convolution of these two in this different order. Right? It doesn't matter. That means that one of the functions can be fixed, whereas the other one can move. It doesn't matter which one you fix, which one you move. Is that clear, guys? All right. Therefore, the response of the system is going to be given by this. The function in time domain evaluated in tau of the input times the function of the system evaluated in tau minus t minus tau. Or you can express this in all the way around. The input, the system, or the system, the input. It depends, it's up to you which one you fix. It's clear for now. What is left? This function here of the input is something that we don't know yet. We haven't established what kind of input, what kind of force is exciting the system. But this one here is already known. Not yet. Because what you know is this. Or, in other notation, how is, well, one notation, this could be a function of omega n, and we have s plus omega n squared. This is another notation. Since we have this as a function of s, we can recover this right away in time. How to do this? This thing here looks like this, doesn't it? And if you check up on the tables, you ended up with this expression. So therefore, in the convolution integral, we can replace one of them, the Laplace transform, the inverse Laplace transform of that thing, is now a function of time. And this is a product of an exponential function and the sinusoidal function. Okay? Let's do this. Go to the equation. And this is something that we don't know, so we're just going to leave it there. But this is something that we do know now. How does this look like? This is beautiful actually. How does this look like? This is one of the best things of using the Laplace transform. Don't you recognize that thing? No. That function there is the product of a function that decays in time and the function that is periodic. So this periodic function with a period equals to 2 pi over omega d. It's multiplied by this decaying function. The decaying function looks like this. And the sinusoidal decaying looks like this. Now you remember, what is the meaning of this thing? This is the response in the free vibration, this is the free vibration response of a system that has some damping. Right? And furthermore, this value has to be between 0 and 1. This is the response, the free vibration response of the system. And here is the input, and we don't know. So convolution says the response in time is going to be related to the free vibration response of the system. And that's the great thing. Because there should be a particular function here that tells us that the output is going to be the same as the free vibration response. But we are going to analyze this later. Great. Let's work this out. Given the response in the form of convolution, which is this one, let's represent in a graphic form the response of the system due to a harmonic input, provided that we have no damping. If we have no damping, what happened to this? One, right? Just like this is not there. Furthermore, what changes? What happened with this omega d? This becomes omega n, the natural frequency. And this one as well. And given this function of time, what happened with these guys? What is this? It's the same. This is cosine, F-O, cosine, omega t. Is that it? Not yet. This is not defining time. This is defining time minus t. Minus time. There you go. This looks better. Alright, guys? So the question is, can you do that if this force excites the system with the driving frequency equals to the natural frequency? What changes? This becomes omega n. Let's see what we can have. For the first case, the solution of the equation is given by this integral. And what is the first case? First of all, this is equal to 0 for all of them. And second, omega equals omega n. So therefore you got omega n, omega n, omega n. Right? So we can say that this is a stationary function, and this is the function that moves. In order to make the product, create an area under the product, and that area is going to be just the integral of the whole thing. We don't need to do that. Somebody has done it. Look how beautiful it looks. This curve in red is the input that is shifted and starts moving depending on the value that tau takes. So when this moves, you can perform the product of the blue curve and the red one. And the product is expressed here at every time. Can you see it? For example, when this overlaps, when the two of them overlaps, for example here, the product is maximum. And you can see there are places where the product is going to be 0, right? For example, this time this is 0, they become 0. This is the product of the function that's being created in the time domain. Now let's take the area under the curve. This is the curve, this is the maximum area. Here this is the minimum area. Here the whole area cancels out. And we start plotting it. This is what is being plotted here. Does it make sense? Does this response make sense, guys? What is the meaning of that response? If you excite the system with a driving frequency equals to the natural frequency, and you have no damping, what happens with the oscillations? They increase in time indefinitely. You can see that these vibrations oscillate, creating time. Is that clear, right? This is just a visualization of what we have. And actually, you can just use the formula, put it in a computer, perform the integration. Let's work out the example when omega equals 0 and still we have no damping. The function was given by this. This was the function, right? Now, let's put 0 here. What occurs with this? This just becomes a constant, right? In this definition, we are going to switch between the fixed and the moving function. The reason for this is, since this is a constant everywhere. You cannot just start moving it because it's a constant everywhere. However, this one will be something that can be moved. Right? So in order to avoid that, let's split them. Use the commutation. And there we go. Now this is the one that is going to move, the sign. And the one that's fixed is this one, and this was 1, wasn't it?
Yep.
I forgot to put here, this is just 1. There's no need for it. And let's see how it looks like once you perform the convolution. This is the constant that happened to be fixed and start moving. What happened? Eventually the area is maximal. Here this minus this cancels, becomes 0, and then it starts growing again. Right? And this area starts cancelling with this one. That's why the whole area reduces. And here you get 0 because these two are equal to this one. And keep doing it over and over. What is this? Does it make sense, guys? This is the response of the system subjected to a constant force. Right? Remember, you have this mass, you have this, and you have no damping. What happens once you apply a constant force? This moves upwards to a new equilibrium position. Doesn't stay there because this has some velocity. Moves still upwards and bounces back. And continues this motion in a new equilibrium position. We demonstrated this with a more simplistic approach if you want. Alright? Any questions, guys? No questions? Perfect. So if you still are not happy with the convolution, plenty of information online that you can check. You can go to books on differential equations, you can go to books on vibrations, or books on dynamic of systems, and there will be a good explanation. What happened with this? Constant becomes just a pulse. This is something interesting. The more that this reduction is, have a look to this. Look, something interesting. Try to find a pattern. This black line here represents the convolution, whereas this is one of the functions, and this is the other function that starts moving. You can see the area created in yellow, and here you're plotting these results. What do you think will happen when this width becomes smaller and smaller and smaller? What happened with the black curve? It gets closer to this one, isn't it? Let's have a look. This black curve is different to this one in this region, which is equal to the width of the function. Make this function smaller in width. This black curve tends to this one. That's the best property of convolution. We're going to cover that next week. That doesn't mean that the class finished. That means that we are going to pay more attention to what's happening. This pulse becomes smaller. One of the best approach. Now, if this was the transfer function, and you get an input and you get an output, this could be also be defined for harmonic inputs, for harmonic outputs. Because whatever is here is a property of the system. It does not depend on whether you have an input and output. Right? So you have this input, this output. I happen to put the notation in the complex form, and this is just a magnitude. I want to save some time. Here's the magic, guys. This transfer function was just defined in the frequency. Instead of S, let's just put I omega. And now this is called the transfer function in the time domain. Right? Any questions? No questions? This is the transfer function in the complex form. This is the transfer function just in the time domain. If you remember, we defined already S to be some real value plus some imaginary value. We deliberately put this omega because if we get rid of the real part, you ended up with a transfer function in the time domain. And what is this, guys? The FRF, the frequency response function. The frequency response function is no other thing than the transfer function in the time domain. It's great, isn't it? We are defining properties of the system, and these properties eventually allow us to not make the problem more complex, but to analyze further issues that might help us to understand better about the dynamics of the system. Right? Here's a video. Let's see whether we can draw some ideas.
The frequency response can be calculated from the system's transfer function.
This is the system response frequency function. This whole thing in column is the transfer function in the complex space. The transfer function is just the projection of the transfer. The FRM is the projection of the transfer function in the imaginary part.
These two axes.
Right?
Input.
So this is the only thing I wanted to show. The whole thing here is the transfer function in the complex plane. The complex plane has an imaginary part and a real part. If you plot it, you ended up with some curve like this one. But if you care only on the direction for the complex part, you ended up with this line, the profile of this transfer function. And this profile is just the same as the frequency response function, right? So this is embedded into the transfer function. All right? It's beautiful, isn't it? Now, in this couple of minutes, let's talk about another chap who was involved in French Revolution, Jean-Baptiste Fourier. Have you heard about this guy? Where? Last semester. Where? You haven't? Advanced mathematics or anything like that. So there are the Fourier transform or the Fourier series. What are they? If you have a signal or a function like this guy said, any function, anything, exponentials, a parabola, a complex function, whatever function can be represented as an infinite summation of harmonic signals. And this harmonic, all of them have a particular frequency, a particular amplitude, and a particular phase. Right? Phase means where you start measuring it. Amplitude, how big the signals are, and frequency, how distant these two peaks are. Right? And he said, well, look, you have this complex function, don't worry, make it easier. Let's assume that this is an infinite summation of independent or individual harmonic functions. And when you say, thank you, my problem becomes even more horrible. Because if this was difficult to analyze, how can you analyze an infinite set of data? Well, that's the beauty of this. Let's see if we can listen to this. Can we? No, because the pitch is very low. Anyway, this is a harmonic function, and this is another harmonic function, and you can add them up. Let's put them together. And what you get? Sum this one plus the one at the bottom, and you ended up with something like this. So the more harmonics or the more different functions, you might have something looking different. But anyway, there is a good characteristic of this. It is periodic. Because some things repeat in time. Depending on the amplitude or the phase, you can see that the shape, that one on the top, changes. Okay? And this is by far the most important concept in analysis of vibrations, which is the spectrum. Right? A good engineer who eventually happen to say that he's got some expertise in vibrations, it's because he handles, or she handles this. What's the meaning of this? Look at this curve in the time domain. This curve is an infinite summation of different harmonic signals with different amplitudes and different frequencies. And if you happen to know how those signals look like, you can see this in the frequency domain. You start from 0 here, and here comes to the plus infinity. What is the meaning of this spectrum? Only this. Here is the spectrum. What is the meaning of this? Here tells you that this signal is composed by this harmonic that has this amplitude and this frequency, plus this one here, this harmonic that has this amplitude and this frequency, plus this one here that has this amplitude and this frequency. Alright? And this bit here is what we call the spectrum of the signal. Next week we are going to deal with our the test, right? Test number 3 on Tuesday, 4 p.m. sharp. And then we are going to do the revision of the test, and then when we have time, we will start again this analysis in the frequency domain as an introduction for general loading.